In this second lecture, I will talk about the discovery of X-rays and radioactivity and also how radioactive sources were used to discover the nucleus and particularly how the tiny nucleus was discovered by so-called Coulomb scattering, or now it is known as Rutherford scattering. Okay. So, on the right you see a picture of Rontgen. In 1895, quite accidentally, he found that a phosphorescent screen which is shielded from a running cathode ray tube glows. So, he was quite amazed by this, and then he inserted a blocking plate, and of course the glow disappeared. So, he followed up by doing this exposure on various items, and one of the items of course was his wife's hand. Uh, he exposed it to this unknown radiation, unknown at that time, and backed it up with a photographic plate. And so on the right hand side below the photograph of Rontgen, you will see the first published X-ray picture of his wife's hand, which has a ring on one of the fingers. This was quite remarkable for its time, and it in fact got a lot of publicity in Europe and elsewhere. And he was the recipient of the first Nobel Prize in Physics in 1901 for this discovery. So, Nobel had instituted the Nobel Prizes, which were initially for physics, chemistry, and physiology and medicine, and he was the first physics Nobel Prize laureate in 1901. Okay, this was followed fairly quickly by the discovery of radioactivity. Henry Becquerel had placed photographic plates next to various phosphorescent materials. He was basically following up on the work by Rontgen, and he found all of them, or almost all of them, were unaffected except those that were exposed to uranium salts. And this was the discovery of spontaneous radioactivity. This is a word coined by Marie Curie, who we will come to in the next couple of slides. So, for this discovery of radioactivity, Henry Becquerel got the Nobel Prize in 1903. Of course, he shared it with the Curies. So, you can see that photographic plates were fogged by the exposure to radiation from a uranium salt. For instance, the shadow of the Maltese cross, you can see a very Maltese cross, of course, the picture of that is shown on the left. Red background and these white elements which have fourfold symmetry. Their shadow is seen here, and so if you insert that Maltese cross between the plate and the uranium salt, this is visible. Of course, it is barely visible. It is not such a great photograph, but anyway, it was the first evidence that there was some radiation which was being emitted by naturally occurring salts. And so this, as I said, led to the discovery of radioactivity. Marie and Pierre Curie worked on these so-called, in those days, they were called Becquerel rays. This is the first time they were found. And Marie Curie and Schmidt found that thorium also emits radiation like uranium. They, in fact, used an electroscope, which is shown here below, where there are two gold leaves which are charged, and the top is grounded, so you have a finite charge on the leaves, and they repel each other. But if you expose it to radiation, then of course there's a now we know that the ion pairs form, and then the electrons actually discharge the positive charge there, and so this leads to the gold leaves coming together. So this is a sort of demonstration of the fact that there is something going on in these Becquerel rays which emitted radiation, which changed the situation in the air around the electroscope. Okay, so they found that pitch blende, which is a ore of I think mainly it has coal in it. This is about 4 times stronger. Uh, I mean, than the uranium, uh, which was emitting radiation, obviously, and the thorium salts were uh, more radioactive than the uranium. They, or whatever is contained in those, had more radioactivity. So they finally isolated these by actually bringing down the amount of material from tons to micrograms, and they separated radium and polonium, of course not at exactly the same time, but they this was identified by the Curies as the source of radioactivity. And when they did that, they found that this is about 1,000,000 times stronger in radioactivity than uranium. Okay. Uh, the source of energy, of course, they measured. So this is the heat emitted in radioactive decay. In radium, for instance, it is about 100 calories per gram of radium. So for this and some other works that they did, but mainly the isolation of the main ingredients of these Becquerel rays, which caused Becquerel rays, they were awarded the Nobel Prize in 1903. So they shared, the two Curies, Marie Curie and Pierre Curie, they shared the Nobel Prize with Becquerel, Nobel Prize in Physics. These are the references, the original references. Willem Röntgen, this is in a journal which is no longer exists now. It's in German language, and this was in 1895, and he published another paper in 1896. Becquerel published it in Compte Rendu in 1896. Also, the Curies published in 1898, 99, and then there was a review which was published by Marie Curie in 1899 and 1900. The nucleus was discovered using these radioactive sources of radium. Uh, in fact, Marie Curie was quite generous with these sources, and she would give these sources to the scientists who she knew would need it. And so Rutherford got his source from her, and he carried out a series of experiments which led to the discovery of the nucleus. So the experiments are the following. He basically asked Geiger and then Marsden to measure the scattering of alpha particles of several nuclei, including gold. And this was done in a series of experiments in 1906 to 1913. And most of the scattering, of course, occurred at small angles, but some through large angles. So the apparatus that they used was the following. There was an alpha particle source, and this was collimated using a couple of collimators, and then this collimated beam fell onto very thin gold foils, such that the alpha particle did not lose too much energy in the gold foil itself, and then got scattered to various angles. So this is the theta, this is the angle of scattering, and fell onto a scintillator screen. Okay, generally zinc sulfide, but there are various kinds of scintillators that you can use to code the screen. They used, I think, zinc sulfide, and then this was looked at through a traveling microscope. So they actually counted one by one the number of scintillations that occurred, and they noted the place where it occurred. So that gave a measure of the angle, and so they could measure the number of events that occurred at a given scattering angle. The alpha particles that came off the radium source getting scattered onto a gold foil and through an angle theta. They published a series of publications, first describing the technique, and then Rutherford, of course, has this important paper in Philosophical Magazine where he puts forth this idea that there is a compact, positively charged entity in the atom, which is much smaller than the. So he proposed this idea of Coulomb scattering, and this was measured by Geiger and Marsden. I'll come to this figure maybe a little later. So Rutherford actually calculated the probability of scattering of alpha particles, which have, let's say, a charge Zpe in units of the electron charge, and of a charge Zt, where Zt is the uh, atomic number of the target atom, and E is again, as I said, electronic charge. Then the differential cross section, or which is related to the probability that the alpha particle scatters through an angle theta, is proportional to the square of each of these charges, the alpha particle charge, electric charge, and the target electric charge, and inversely proportional to the sine to the power of 4 of theta by 2. And this calculation used just classical mechanics. So, this figure shows that you can come in asymptotically at a certain angle and then get scattered. So, this parabolic trajectory is the trajectory of the alpha particle, and the nucleus is sitting somewhere here, and this is the you can define this in terms of the impact parameters and so on, and he got this equation, the scattering cross section, the differential scattering cross section, which is inversely proportional to both the energy squared and the fourth power of sine theta by 2. It is interesting to note that this was a classical calculation. Quantum mechanics had still not come. It was another 14 years before it would come. And this formula holds even in quantum mechanics for non-identical particles. J.J. Thomson measured the beta scattering earlier and found only small angle scattering. So, indeed, small angle scattering dominates even alpha scattering, alpha on a gold target scattering. But Thomson did not go further and measured large angle scattering. This was done by the instigation of Rutherford, and indeed they found large angle scattering, which is what led to the discovery of the nucleus. Rutherford and Geiger, of course, decided to repeat this experiment of J.J. Thomson, which was done with beta particles, with the much heavier alpha particles. And so, when they found large angle scattering, it had to be its origin had to be some extremely strong electric field which can exist at just close quarters to a compact object, and that was what was found to be the nucleus. Okay, before I go that, maybe I should go back in my slides to the earlier figure which is shown here, which shows the scattering probability, or the scattered alpha particles, as a function of the scattering angle given here in degrees, 0 to 140 degrees shown here, and this the number of scattered particles here. Okay, this is in some arbitrary scale. Obviously, they didn't count into the 7 particles. This is on some arbitrary scale. So, you can see that if you have a point object, then this is the kind of distribution that you get. The number of particles scattered at an angle theta with respect to theta. If, on the other hand, the charge is extended to, let's say, the size of a, let's say, of an atom, or a fraction of an atom, 10 times smaller than an atom, then you get a much faster falling scattering probability. Okay. So, the fact that you have large angle scattering, so this is the key. It is not the small angle scattering that tells you very much. It is the large angle scattering, because small angle scattering corresponds to large impact parameters. Okay. Whereas large angle scattering corresponds to small impact parameters. That's when the projectile comes closest to the target, and that's so. If you have a very compact entity in the atom, then you have large electric fields, and that leads to large angle scattering. So, this is what the experiment demonstrated. Okay, so we have these two models. The Thomson model, which was there at that time, it was called the plum pudding model. So, you have the atom, and embedded in that are electrons, and then you have a distribution of positive charges to balance this out, and then this would lead to only small angle scattering. Whereas, the Rutherford model said that you have a compact nucleus and you have electrons around this, which actually form the size of the atom, which is of the order of an angstrom, and this nucleus is about 10,000 times or so smaller than the atom. So, coming back to the experiment of Geiger and Marsden, they actually found that 1 in 8,000 particles, alpha particles, scattered at angles greater than 90 degrees of a very thin gold foil. Okay. That was the key observation. Of course, they got the whole distribution as well with some statistics. So the conclusion was that the positive charge is concentrated in a much smaller volume than that of the atom. So the nuclear radius is at least of the order of 10,000 times smaller than that of the size of the atom. Okay. So in the Thomson model, this is pictorially shown here, you have a source of alpha particles, you get mainly small angle scattering. Whereas in the Rutherford model, you have alpha particles mainly scattered at small angles, but you have a few events coming out at large angles, and this is the key to our understanding that there is a compact nucleus. The event rate for such events is small, the probability is small, but nevertheless, the fact that it is there shows us that there is a compact nucleus. Okay, so this is some of the data taken from their publication in Philosophical Magazine in 1913, the laws of deflection of alpha particles through large angles. So you can see that as a function of the angle of deflection and 1 by sine to the 4 theta by 2, then this matches n by sine 4 theta by 2 is sort of roughly a constant. Okay, and from 15 degrees to 150 degrees. Okay, and then there are other quantities that are also put in there. You can see the kind of statistics they have, something like 132,000 at small angles and about 30 odd at large angles of about 150 degrees. Okay, and so they show the number of scintillations per minute for various targets. For the lightest targets, they did this experiment with aluminum, copper, silver, and so on. But the most spectacular one, of course, is the one on gold. This effect, of course, is there in all of these, atoms, scattering from all of these atoms. So, the summary of these set of experiments is that the variation of alpha scattering event rate by probability is measured with respect to the scattering angle, and it goes like cosecant to the 4 theta by 2 or inverse sine to the 4 theta by 2. It is directly proportional to the target thickness within, of course, a limited range. Of course, if you put too thick a target, it will stop or radically change the energies that comes out of the energy of the alpha particle that comes out of the target. They did this as also studying it with various target materials, and it goes, the scattering at large angle actually goes like the atomic weight squared. The inferred electric charge per atom is about half of the atomic weight in AMU. In terms of the energy dependence of this scattering probability, it goes like V to the minus 4, or as I said, E to the minus 2, as predicted by the classical theory of Rutherford. The other important works of Rutherford in physics is that he, of course, identified the nature of radioactivity, and so this alpha, beta, gamma nomenclature actually comes from Rutherford and Soddy. So he also found that the alpha particle is nothing but a helium nucleus. So he collected whatever comes out of the radioactivity in a glass bulb and did atomic spectroscopy, and he found that this is nothing but the helium atom that is there. Another extremely important discovery that he made was the radioactive decay law in 1902, that all spontaneous radioactivity decays with a certain time time constant, or you might say a certain half-life. A half-life is something that if the decay decreases by a factor of 2, then in that time is called the half-life. And so he found this radioactive decay law, and this actually has the elements of quantum mechanics in it, because such a thing cannot easily be understood within classical theory. He also identified the element now we know as radon. He proposed that there are neutrons in the nucleus to compensate for the proton-proton repulsion, because if you have such a compact nucleus and you have protons sitting in there, they would repel each other. So now what prevents them from exploding? So he proposed that there is a neutral object there in the neutron, and perhaps it binds these protons and the nucleus as a whole. He was actually responsible for inspiring great experiments at Cavendish Lab at Cambridge, which he was the director of. And these experiments included, among others, the discovery of the neutron by Chadwick, or the first DC accelerator which produced nuclear reactions due to Cockcroft and Walton. Interestingly, he used to berate chemistry as a stamp collector's domain, but he got the Nobel Prize in Chemistry in 1908 and was awarded for his investigations into the disintegration of the elements and the chemistry of radioactive substances. As I said, I'll say a few more words about the radioactive decay law. So basically, that all radioactivity, or indeed all unstable, naturally decaying things, decay with a certain decay constant. So the number that remain is given by n, starts off with n0, and then it goes down exponentially as e to the minus lambda t, where lambda is the disintegration constant, and the inverse of that is called the lifetime of the whatever entity you are talking about. The half-life is related to that in that the lifetime is about, let me see, 0.69 times the t half, or the other way around, sorry. Okay, so Rutherford and Soddy in 1902 investigate thorium X, which is now we know as 224 radium, and they plot this decay curve, uh, how the radioactivity decreases as a function of time, and how the daughter activity actually grows with time. The daughter activity grows in exactly a complementary manner. And so the law of decay of the activity with time in all cases appears an expression of the simple law of chemical change. So these sort of things have been seen in chemistry as well, where you have two ingredients and the reaction takes place. So in which one substance only alters at a rate proportional to the amount that is remaining. An example of this is I already talked in the first lecture about carbon-14 being used to date archaeological items, and this is a very nice application of that. But I want to say something which is different also here. Of course, carbon-14 is used to date, and there can be two ways of doing that. You can either count the decays or you can count the carbon-14 atoms. And of course, if you count carbon-14 atoms, it's a much more sensitive way of dating archaeological items because you can count the atoms one by one, whereas if you measure the decay, then the decay rate is small because of the long half-life, and so the sensitivity, of course, is poorer. This is how it was actually found by Libby, but later on the accelerator method was discovered, and that led to a much more sensitive way of dating items. Okay, so the other thing that I wanted to talk about was the so-called Kalfin theorem in 1968, where it was shown on very general principles using quantum mechanics that the decay rate is exactly zero at t equal to 0. Okay, and this was a problem at that time, which was very current. Why do protons? Protons are supposed to decay in many of these unified theories, and why don't they decay? So this was a very current issue at that time, and of course, what is not clarified in the Kalfin theorem is out of scope for that theorem. Is and what time scale does the radioactive decay law set in? Okay, and so it needs to be verified. Therefore. After all, a law is only as good as its experimental verification. So Norman, and we know of course that this was found by doing experiment by Rutherford and Soddy in a certain time domain. Norman in 88 and 95 expanded this domain vastly. So he found that the radioactive decay law is valid for extremely short time scales of the order of 10 to the minus 10 or greater, and also in up to about 45 times the half-life. Okay, and this was done using potassium 40 and 54 magnesium, and to the about to plus minus 10%. So as far as we know, there is no violation of the decay law, although in atomic physics there is something which has been found by experiment called the quantum Zeno effect, and if I have time, maybe in some future lecture I might talk about it a little. Okay, so next I come to discovery of isotopes and measuring atomic masses. The evidence for atomic isotopes from radioactive decay products was done by the work of Frederick Soddy, who got the chemistry Nobel in 21. So these isotopes are basically the same atomic charge, but they have different masses. So this was what was the finding of Soddy, and this was beautifully verified using high resolution mass spectrograph measurements, using the mass spectrograph which Aston developed, and he developed this to get accuracies of the order of ppm, ppm accuracy of the masses, and that was enough to even say that the binding energies can be measured this way. Uh, After that, there was the discovery of heavy hydrogen by Harold Urey, who got again the Nobel in 1934. These are the references below which are given for each of these discoveries. And heavy hydrogen has a particular significance in nuclear reactors which use heavy water as the moderator. So Soddy found that there are decay chains of uranium thorium which are products such as lead, for instance, which are chemically identical but they differ in atomic mass. Whereas in alpha decays, we know 4 atomic mass units are reduced, where hydrogen atom is 1 AMU. So the daughters of uranium and thorium, although they lead to lead, they have different masses. So for instance, in one of the chains, in let's say uranium 238 chain, you get 206 lead, and in the other case you get 208 lead. And this could be easily done using mass spectroscopy, using the Aston's mass spectrograph, for instance. So the preparation of from radioactive minerals of different isotopes of lead followed, and the determination of their atomic weight, spectrum, density, etc. established the same chemical character, but the atomic volume can be also the same, but they have differences in atomic weight. Aston, of course, as I said already, mentioned already, he developed this mass spectrograph. So he was building on the work of J.J. Thomson and Wien, who used a suitable combination of electric and magnetic fields to make a high resolution mass spectrograph. He identified isotopes in neon, chlorine, and mercury. And in fact, he measured the binding energy of nuclear isotopes, because if you can measure the masses to an accuracy of 10 to the minus 5, delta m by m to the of the order of 10 to the minus 5 minus 6, then you can get the binding energy of nuclei. Okay, and so this was called the packing fraction in those days. So you have a charged particle. So the principle is the following: a charged particle moving in electric and magnetic field experiences forces due to the electric field and due to the magnetic field given by the Lorentz force, that's given here. And so when V is perpendicular to B, you can basically momentum analyze, you can energy analyze using the electric field, and you can uh, get a certain velocity using a combination of electric and magnetic fields. Uh, so you get the Wien filter. If you have electric and magnetic fields perpendicular to one another, then you can select a certain velocity. You can select therefore a momentum if the magnetic field is there alone. For a charged particle accelerated by a voltage drop, of course, you have the curvature of the orbit. This can be given by this relationship. And this implies that particles with the same m by q have the same trajectories. The fringe fields of these magnets, which is somewhere here, this is the field is going into the page, then this can bend particles which are collimated, and then also the fringe fields can focus it onto a plate or onto a scintillator plate or onto a photographic film, and then you can record these. And so Aston shows these records where you have let's say isotopes of neon, of course mixed up with other impurities, and similarly chlorine, where you have basically 35 and 37 chlorine coming from here, 35 and 37. The rest of them come from impurities like argon and other elements, titanium and so on. Urey, of course, identified heavy hydrogen. This was following the discovery of isotopes in oxygen. They took a look at hydrogen and measured the Balmer lines, and also they isolated the heavy water, because this has heavy water has a slightly higher boiling point than light water, and so by reducing the volume by about a factor of 5,000, the deuterium content was enriched. But still, this was not enough, and so they had to do this in different ways, and finally they managed to enrich this majorly, and they found that by using certain tricks like boiling at a lower temperature, at a lower pressure, they found that you get a further fivefold increase, and that increased the very faint Balmer line that you get, which is slightly shifted with respect to the Balmer line of the normal hydrogen, hydrogen 1. Uh, and they estimated that the abundance in natural water was of the order of 250 ppm, but they found no evidence for an isotope which is 3 times heavier than hydrogen, namely tritium, which we now know. But that's because it was radioactive, and so that can only be produced on much more tinier scales through cosmic rays, but also majorly through reactors. This is the key paper of their discovery. So, in summary, we have talked about how X-rays and radioactivity was discovered, how the tiny nucleus carrying all the positive electric charge was discovered using alpha scattering on various materials by Rutherford and his colleagues. Large angle scattering is the key takeaway, implied a compact nucleus at the center of the atom. Radioactivity decays spontaneously and randomly, and this follows the exponential decay law. Atoms can have more than one isotope, but they have the same chemical properties. And the first isotope to have been enriched was heavy hydrogen, which we now call deuterium. Thank you.